Hi guys, welcome back to my YouTube channel. My beautiful name is still Nyambura Kibe. Today we're going to go through a unit called Methods of Applied Mathematics. Methods of Applied Mathematics. It's not one of the simplest units, but we will simplify it together. Manze hii degree lazima tuipate by fire by force. And thank you for your continued support. For those who subscribed to my YouTube channel, please watch. Ukiona sijafanya hesabu vile ulikuwa na expect ifanywe, ukiona sija simplify manze, ujue mimi si lecturer manze. Yeah, you just subscribe and at least give me some morale to keep moving, you know. It's not easy for me either, and we're just trying. Yes, so today we will not do a lot on methods of applied mathematics. It's not a broad course. No, it's just a small course. You know, we will just handle the canonical forms of second order linear partial differential equations, and then we'll look at the methods of separation of variables for solving these partial differential equations. Then on the third one we will look at the Fourier series, and under Fourier series we will look at the orthogonal functions, the odd and even functions, the Fourier sine cosine series. Yes, and on the last one we will look at the Laplace transforms. The Laplace transforms will be the last thing we will look at in the methods of applied mathematics. And after this we will look at the inverse Laplace transform and the applications to solving the differential equations. It is as short as that, but I don't know why I'm not finding this unit as one of the simplest, especially in the introduction, the canonical forms of PDEs. Hey, guys, let us help each other here. So let us start. I hope God will intervene and make it easy for us, you know. Hii degree lazima tumalize with the help of God. So as I have told you, we will start with the canonical forms of partial differential equations. Partial differential equations, that is the meaning of the abbreviation PDEs. And here in the canonical forms, it's just a small thing that we will look at as per now. There's no need of looking at a very big outline, and we fail to understand. Yes, so especially in these canonical forms, we will go step by step, and so that too we all understand. So under the canonical forms of PDEs, we will consider a second order partial DE. We will consider a second order partial differential equation yenye iko na two independent variables, x and y, with x and y which are independent variables. I hope we move together. And the general form of this second order partial differential equations with x and y as independent variables, its general form will be a partial u squared partial x squared plus b partial u squared partial dx dy plus c partial y dy squared partial y squared plus d du dx plus e du dy plus f u is equals to g. Kindly look at the general form of this second order partial differential equation first before we continue. It's a d squared u over dx squared plus b d squared u over dx dy plus c d squared y over dy squared plus d du dx plus a du dy plus f u is equals to g. Let us name this equation C1, and we will make a lot of reference to this equation. Yes, and here we say each coefficient, these are the coefficients, each coefficient, let me just write each coefficient A, B, C, J, E, and E, F, and G are the functions of X and Y. I hope we're together up to there. Then we say, having this down, then we say the canonical forms. The canonical form of C1. Remember, C1 is this general equation, are given as 1, the hyperbolic form. We will tackle this in details. This is very important in the introduction part of this unit. Yeah, so I highly request that we all pay deep attention to it. And the representation of the hyperbolic form of the general form of the DE is represented as uxy or uxx minus uyy. That is the representation of the hyperbolic form of the DE. The other form is the parabolic form. The parabolic form is represented as uxx or uyy. I hope you get that difference between the two. Now, the third form is the elliptic form. And the elliptic form is represented as uxx plus uyy. I hope you familiarize yourself with these forms. Yes, the hyperbolic form is represented as uxy or uxx minus uyy. The parabolic form is represented as uxx or uyy. The elliptic form, on the other hand, is represented as uxx plus what? Plus uyy. Now, the parabolic form is also, you can, if you see the hyperbolic form of a DE, it forms the wave equation. Yes. On the other hand, the parabolic form, it forms the heat equation. Yes, I hope we're together up to there. And then the elliptic form forms the Laplace equation. I hope you're together up to that point. Yes, it's not as easy as I should argue as in the representation of the wave equation. The wave equation is represented as d squared u over dt squared is equals to du over dx squared. Yes, that is the representation of the wave equation. On the other hand, the heat equation, or the parabolic form over dE, is represented as du over dt is equals to du plus dx squared. And yeah, that's generally the representation of the heat equation of the or a parabolic form over dE. Lastly, the elliptic form, or the Laplace equation, is represented as just this. So the equation, remember, an equation must have the symbol is equals to. Without the symbol equals, that is not an equation. So representing the Laplace equation, we represent it as uxx. I think this is the simplest because you will only need to remember this, and the equation becomes that. Yeah, it's not hard, even a little bit. Yes. Today I don't want to do so much. No, this is not one of the easiest topics in this unit. So I just wanted to do a short video about on the introduction concerning the canonical forms of partial differential equations. Yes, and just look at this and create a basis of this unit with that one. See you in the next video. Ciao.